Now that we have an idea of what parametric curves are, how do we get calculus into them? Now remember, up until this point, we've defined two new functions, x as some function of t and y as some function of t as well. So what does it mean to find the derivative of this function? Well, it actually has the exact same meaning. And you can kind of get the idea of this if you think about the graph itself. Remember, our graph looks exactly the same as it always would in terms of x's and y's. So if we're looking for a derivative here, we're still looking for the change of y with respect to x. So what we're looking for is what does dy dx equal? Which would be what? The change in y over the change in x. Well, the exact same idea comes into play here. So we're still looking for the change in y with respect to the change in x. But now y is a function of t. So y changes when t changes. So the change in y would be the derivative of y with respect to t. Now, I don't want to put the d there, that's a bit wrong. Let's just call that the change in y. Right? The change in y would be the change in y with respect to time. Same thing with the x. The change in x would be dx dt. So this is going to tell us how much y changes and how much x changes. So if we're looking for the change in y over the change in x, now this is in infinitesimal case, we'd have dy dx is equal to the change in y, dy dt over dx dt. And that's actually what our derivative would be when it's in parametric form. Now notice just algebraically, we have dy dt divided by dx dt. If you flip and multiply this, you get dy dt times dt dx, which is dy dx. So you can see just kind of algebraically how this would make sense. So if I wanted to find, it's just a quick little show there. If we wanted to find the derivative, what you have to do is you find the rate of change of y with respect to t and divide it by the rate of change of x with respect to t. Now there's a few subtleties here that makes the second derivative confusing for a lot of people. Here we're assuming y is eventually a function of x. So y, technically for all this, y is what we're looking for the change in with respect to x, which means that's our function we're taking the derivative of. So what would the second derivative be? So I'm going to go up here, I'm just going to move it up here so you can see it a little bit better. dy dx we said was dy dt over dx dt. So what would the second derivative be? Well, kind of think about how we did the derivative of this. Y was our function we're looking for the overall change in. So we did the derivative of that function with respect to time and then divided it by dx dt. So that's our format for how to take the derivative. We take the derivative of the function with respect to t and divide it by dx dt. So anything we want to take the derivative of, here's what we would do. We take the derivative of it with respect to t and divide it by dx dt. But for our second derivative, what are we trying to find the derivative of? Well, the first derivative. So that would be dy dx. And then for the third one, the third derivative would be the same format. So the third derivative of y with respect to x. How do we take the derivative? We do the derivative with respect to t of what we want, divide that by dx dt. So the third derivative would be the derivative of, well, the second derivative. Okay, so the idea of how a derivative is taken in parametric is a little bit different. You take the derivative of the function you're looking for with respect to t divided by the new independent variable, right? We're saying x is the independent variable here with respect to t, and you keep doing that over and over and over again. So let's just try a few of these. Let's do find the slope of the tangent line, let's say, and the concavity of, let's go, how about x is equal to t squared, y is equal to, let's make it easy, how about t cubed? and let's say at the point 4, 8. Okay, so we got a lot to unpack here. First off, we're told to find the slope of the tangent line and the concavity, which means we're going to need both the first and the second derivative. So let's go after the first derivative first. So for the slope of the tangent line, we're still looking for dy dx. Well, from what we just learned, dy dx is really just dy dt over dx dt. Now both of those are just Calc 1 level derivatives, super easy. The derivative of x with respect, the derivative of y with respect to t is 3t squared. The derivative of x with respect to t is 2t, so that's going to be 3/2 t. All right, for our second derivative, how do we find our second derivative? Well, that's the second derivative with respect, second derivative of y with respect to x is going to be the derivative with respect to t of our first derivative, which is 3/2 t, divided by dx dt is still 2t. So let's see, the derivative of the top is just going to be 3/2 divided by 2t, so this is 3/4t. Okay, so there we go, we got our first and second derivative. So if we're looking for the slope of the tangent line, we're looking at our first derivative. But notice, this is the second point that a lot of people make mistakes on. This is a function of t. However, the point that we're given is an xy value, right? We're given, we want to know where all this is happening at the xy value for 8. So now you got just a little bit of algebra to try to do. You got to figure out what t value gave you that point. So a lot of times you can just do this in your head. For what t value would t squared be equal to 4 and t cubed be equal to 8? Well, hopefully that's obvious. That's when t would be equal to 2. And you can do this by kind of elimination. Solve the first equation for t. Notice that gives me actually plus or minus 2, but only the positive 2 works in the second equation. Okay, so we now know that at t value of 2 will give us the slope and the concavity when we plug it into the first and second derivative respectively. So the slope of our tangent line will be 3/2 times 2, which is 3, and the concavity, if I spell it right, will be equal to 3/4 times 2, which is 3/8. Okay, so there you go. So notice, other than taking the derivative a little bit different than what we used to, the idea for finding slope and concavity would be the exact same thing. Plug it in the first derivative for the slope, second derivative for the concavity. All right, now we also can talk about things we did back in Calc 1 with this, things like horizontal tangent lines. But we can also now do something we didn't or couldn't do in Calc 1. We can actually talk about vertical tangent lines. Because in Calc 1, we generally only dealt with functions, which means they would pass a vertical line test, which means they would never have a spot where you could have a vertical tangent line. However, if we're talking about something like a circle, this is not a function, right? Will not pass the vertical line test, but would have a place where it has a vertical tangent line. So, good news is the idea is exactly the same for horizontal tangent lines. Well, for a horizontal tangent line, I'll draw one down here at the bottom of this. What do we know about here? We know the slope is 0. So if you think about the slope, dy dx, the slope to be 0, that means for a fraction to be 0, the top has to be 0. That means the change in y is 0, and that makes sense because we're not moving up and down at all at this point. It's flat. Now, in terms of our new derivatives, we know the change in y is actually dy dt, and the change in x is dx dt. So for us to have a horizontal tangent line, the change in y has to be equal to 0. Now for a vertical tangent line, what's the slope of a vertical line? Well, it's undefined, which means we'd have to have a 0 in the denominator. Now again, same idea. For our vertical tangent line, we're not moving in the x at all. Kind of think about it. We were moving in the x this way, then we stopped and we started moving in the x that way if we were kind of coming around the curve this way. right? Or this way, we're moving to the right, we're moving to the right. We stop moving left or right at all, then we start moving to the left. So the idea for this, let's get our picture out of here, for a vertical tangent line, dx dt has to be 0. Now, in general, they're going to add something else into here. For horizontal tangent line, we want dy dt equal to 0 as long as dx dt, I'm messing up my t, is not 0. And the same thing over here, we don't want the other one to be 0. Now, why is that true? Well, that actually gets us into another definition, which is generally somewhere around this section of your textbook. It may not be in yours right now, but the idea of something being smooth curves. Smooth is not a really easy definition to talk about. What does it mean to be smooth? Most people say, oh, well, that's a smooth curve. That looks pretty smooth to me. The idea for a smooth curve, and you may have seen this in Calc 1, is the idea that a graph has no sharp points in it, right? This is nice and smooth, whereas a graph that kind of looks like that would not be smooth at that point because it's got a sharpness there. Well, what's happening at a sharp point? Well, notice in this picture, you know, like the way we used to draw birds in first grade. Let's just take a look at what's happening to the y values of these points. As we move, I'm going to go from left to right here. As we move from left to right, the y values are decreasing, so they're going down. Then the y values stop going down, and they start going up. So at some point there, dy dt had to be 0. Now also, when we move from left to right, now just look at the x values. The x values are moving to the right, but as we get down to that point, we actually kind of stop moving for an instant and then keep moving again. So also dx dt was here. So a graph is smooth everywhere as long as they're both not 0. So that's why we have this up here. It'll have a horizontal tangent line when the change in y is 0, but the change in x is not, right? Because if they're both, you get a sharp point. And the same thing the other way around. So a curve will be smooth is smooth everywhere dy dt and dx dt are both non-zero. Okay, so the idea, one could be 0 or the other can be 0, that's fine. That just means you're going to have a horizontal tangent line or a vertical tangent line. However, if they're both 0 there, you end up with a sharp point and you don't get a horizontal or vertical tangent line. And at that point, we say the curve is not smooth. All right, the last thing I want to talk about in this section is actually old material. We're really just going to get 2 brand new formulas that we've already seen in the past. So I'm really just going to give you the formula again. 2 things that we've seen in the past for curves was we saw arc length and we saw surface area of revolution. So I'm basically going to show you how those formulas show up with parametric. So remember when we were talking about arc length, super quick review. We had some curve there when we decided to zoom into a little area like this. Picture doesn't match what I'm getting ready to draw though. We ended up with a super short piece of arc length, which we called d little s. And to figure out what that was, we made a triangle and we said this side would be dx, that side would be dy. And we came up with an expression for ds, which was this. Using your Pythagorean theorem and solving, we got ds was the square root of dx squared plus dy squared. All right, so super quick one on that one. So what did we do next? Well, it kind of depended on, did we want to treat our function as y as a function of x or x as a function of y? To do that, what we would do is either divide out the dx squared or divide out the dy squared. Well, in parametric, we got a brand new variable dt. So we need to do this a little bit different. Here's what I'm going to do. I'm going to kind of cheat here. I'm going to call this ds. On the inside here, dx squared plus dy squared. I'm going to multiply by a funny looking one. I'm going to multiply by dt squared over dt squared. Now the bottom dt, I'm going to go ahead and distribute into this piece. So ds will be the square root of dx squared over dt squared plus dy squared over dt squared dt squared. Oh, forgot me. All right, now I'm going to leave the bottom one inside here, but I am going to take the square root of this. Now this would give me the absolute value of dt, right, because we're taking the square root of it. But again, we're going to assume that, that's a b, that our parameter runs in a positive direction, so the change in that would also be positive. So I can say that ds dt is the square root of dx dt squared dy dt squared dt. So this is an idea of what a tiny little piece of arc length would be. So if we wanted to have the full arc length, we would just integrate over the region we're talking about, a to b. Now a to b here is for the parameter of t, right? That's what t runs from, of the square root dx dt squared dy dt squared dt. And there you go. That's our new arc length formula when we're in parametric. So again, it's just a formula. You're going to be given x as a function of t, y as a function of t. Just find each derivative, plug it in, and try to integrate. Like always, arc lengths, they're generally pretty hard to integrate. So the integration at this step is going to be pretty tricky. The other thing that we did was the surface area of revolution. Basically, if you remember, I probably drew a picture something like this. Let's see, this marker's dying. The idea is we have some two-dimensional curve, looks something like that. Let's go out to some point. What happens if I take this and I revolve that around the x-axis? What would the surface area of that give us? Remember, the way that we did this is we took a little strip out of here. Let's see, think about that as our axis. We took that little strip and we rotated it around the x-axis, and we got kind of this ribbon shape. Put it like that. Then we cut that ribbon shape out and we got this strip. We saw that this side was a small piece of the arc length, so we called that a little piece of ds, and this was the circumference of that circle, and that circumference of the circle was defined to be that distance there away from the axis of rotation. So we know the circumference is 2 pi r, that radius, and that radius, if we're going around the x-axis, would be whatever x of t is or y of t. So that was it. So we could see that, let me go ahead, I'm gonna get this out since we've done this before. So we can see a small piece of the surface area would be 2 pi r ds, right? Just length times width of that rectangle I just drew. So dsa would be, well, 2 pi is going to be a constant, so I'm going to end up pulling that out front. The radius, well, the radius depends on what we're revolving around. If we're revolving around the x-axis, that would be our x of t. I'm going to put x of t. And ds, well, we know what ds is. We just did that 2 seconds ago. There's our definition of ds. This will be the square root of dx dt squared dy dt squared dt. So for all of it, the surface area would be, again, pulling the 2 pi out. Now again, our parameter would go from a to b, so this would be x of t square root dx dt squared plus dy dt squared dt. This is about the x-axis. And the only difference about the y-axis is what our radius would be, right? Our radius would be measured this way, so that would be y of t. Oh, I got this backwards. I'm sorry, everybody look. That would be y of t, that's a y distance. Yeah. I don't know why I said x. That would be y of t, right? This is a distance in the y direction there, so that would be your radius. And the other one, again, the same formula for measuring from the y-axis. That would be our x distance, so that'll be x of t. Square root, same thing, dx dt squared dy dt squared dt. It's about the y-axis. All right, sorry, it's kind of squeezed in down there. It is just two formulas though. Now the good news, remember, with our surface area formulas, it's a more complicated looking formula. However, it's generally easier to integrate. So the reason is because now you have something for like a u/du substitution there. All right, so two old formulas that I just updated to our new type of parametric equations. So it is just a formula, so see how well you can do with those.